Welcome back to the deep dive. Today we're going deep into the world of AI efficiency.
Oh, very cool.
Specifically, how researchers are trying to make these AI models that we keep hearing about so much
Yeah.
more efficient.
hmm
And you actually sent in this paper about tuning transformers into RNNs.
Yeah, it's pretty wild stuff.
And it's all about speed.
That's right. It is all about speed. It's kind of like think of it like this. Transformers are like high-performance sports cars.
Okay.
Super powerful, but they guzzle gas.
Yeah, I can see that.
And then you have RNNs, which are like a sleek electric car.
Okay.
Very efficient, and they can still get you where you need to go.
Yeah,
And this paper is all about like how do we get that best of both worlds?
I like that.
Yeah.
So this paper focuses on making transformers, which are those AI models that are so good at understanding text.
hmm
Even better at generating text.
Right.
But there's a snag, right? They can be slow and memory hungry,
Yeah, definitely.
especially with longer pieces of text.
Yeah.
It's kind of like trying to find a specific book in a library that has millions of books, and you have to go and check every single book.
It's a great analogy, and that's the problem that they're trying to solve here.
Yeah.
So as the text gets longer, the processing time just blows up.
Oh, wow.
It increases exponentially. It's called the quadratic scanning problem,
Okay.
and that's where the need for efficiency comes in. So what they're proposing here with T2R, which is transformer to RNN,
Okay.
is a way to streamline those transformers
Well,
without losing too much accuracy.
So how do RNNs help with this? They seem to be the key to this whole streamlining thing.
Yeah, they work a little bit differently. They have what's called a state that evolves as they're processing text.
Mhm.
It's kind of like having a smaller, more focused library
Okay.
that updates as you're reading, making it much faster to find what you need.
Oh, that makes sense.
Yeah,
But there's got to be a trade-off, right? We can't just magically get all this speed without giving something up.
absolutely. You're right. RNNs might not capture every single nuance
Okay.
that the original transformer could. It's like, if you're choosing a more fuel-efficient car, you might have to sacrifice a little bit on horsepower.
Oh, yeah, that's fair.
So the real challenge of this paper and what they're trying to do is strike that balance.
Right.
How do we get the most efficiency without losing too much accuracy?
So they're looking for the AI equivalent of a hybrid car.
That's a perfect way to put it.
So how do they actually transform a transformer into an RNN?
So with their method T2R, they're essentially replacing part of the transformer's attention mechanism with something much simpler.
Okay.
It's kind of like trading in, a complex multi-step process
Yeah.
for a one-step solution. And what they use is what's called an MLP feature map.
Hold on. MLP feature map. Can you break that down for us?
Sure, it sounds really complex, but at its core, it's basically a way to condense information
Okay.
from the text into a more manageable form. Think of it like a super efficient note-taking system,
Okay.
where you're just highlighting the most relevant parts of a textbook.
Oh.
And this allows the RNN to process information much faster and with less memory.
So they're teaching the RNN to focus on the important stuff without getting bogged down in all the details.
Exactly. And what's fascinating is they don't explicitly tell the RNN how to do this.
Hmm.
It's not like they're programming it, step by step to mimic the transformer's attention patterns.
Right.
They simply allow it to learn these patterns on its own during this process called fine-tuning.
Wow. So the RNN is essentially like reverse engineering the transformer's knowledge.
It really is quite remarkable.
So how well does this actually work? I mean, did they actually manage to speed things up?
They did. It's really impressive. The paper focused on two key tasks: language modeling, which is like predicting the next word in a sequence,
Okay.
and machine translation.
Got it.
And in both cases, T2R significantly boosted speed and reduced memory usage.
Wow.
They even outperformed other linear transformer approaches that are also trying to be more efficient.
That's amazing.
Yeah.
So are we ready to run complex language tasks on our phones without them overheating?
Not quite there yet. While the results are really exciting, there's still a small accuracy gap
Okay.
compared to the full transformer. Think of it like we're most of the way there on efficiency, but still need a few tweaks.
A work in progress, but definitely moving in the right direction.
For sure.
Now, you mentioned they analyzed how attention patterns changed after applying T2R.
Yeah.
What exactly did they discover there?
So this is where it gets really interesting. The fine-tuning process actually helped the RNN learn attention patterns that were very similar to the original transformer, even though they didn't program it to do that explicitly.
That's incredible. So it's learning by observing, not by direct instruction.
That's right. It's like, watching an apprentice learn from a master craftsman just
Yeah.
by observing their techniques.
That's so cool. And the focus of this episode is like getting into the mathematical nitty-gritty of the paper, right?
Absolutely. This research really highlights the potential of leveraging pre-trained models and how we can kind of refine them for specific tasks, making AI more accessible.
Yeah.
And the real magic of this approach really lies in the mathematical foundation of how they achieved this.
Okay, now I'm really intrigued. Ready to get a little more technical?
Definitely. Let's unravel the mathematical elegance behind this T2R method.
Let's dive into part 2 then.
Welcome back to the deep dive. In part 1, we were talking about how researchers are transforming these power-hungry transformers into lean, mean RNNs
Right.
using this method called T2R.
Mm-hmm.
And now we're going to kind of delve into that fascinating mathematics behind this approach.
Okay, I'm ready to put on my math thinking cap.
All right.
But just remember, I'm more of a concepts person, so try to break it down for me.
Absolutely no problem. So remember how we talked about the attention mechanism in transformers?
Yeah.
It's basically their way of focusing on different parts of the text.
Right.
But it can be very computationally expensive, especially when you're dealing with long pieces of text.
Right. It's like they're trying to analyze every possible connection between words in a sentence.
Yeah, that's a really good way to put it. So the traditional attention mechanism, the way it works is it calculates the relevance of every single word to every other word in a sequence.
Wow.
It's kind of like creating this massive spreadsheet where each cell represents the relationship between two words.
Oh.
And you can imagine how that gets really complex really quickly.
Yeah, no wonder transformers can be so resource intensive.
Exactly. And that's where the brilliance of T2R comes in.
Okay.
They simplify this process without sacrificing too much accuracy, and they do this by replacing the computationally intensive part of the attention mechanism
Okay.
with a more streamlined approach.
I'm intrigued, but how do they actually do that? What's the secret sauce?
They use what's called a feature map. Think of it as like a special lens that changes how the model sees the text. So instead of looking at each word in isolation,
Right.
this feature map lets the model focus on higher level patterns and relationships.
So instead of getting lost in the weeds, it's looking at the forest as a whole.
Exactly. And this feature map is designed to work really well with RNNs. Remember how RNNs have that state that evolves as they process the text?
Yes, it's like their internal memory,
Yeah.
Keeping track of what they've learned.
Yeah, exactly. And the feature map basically enables this RNN state to capture the most important information from the text
Okay.
without having to store all those individual word relationships.
It's like the RNN is taking notes, but only writing down the key points.
Perfect analogy, and this is where we get into the math.
Ooh.
They use a specific type of feature map called an MLP feature map,
Okay.
which stands for multi-layer perceptron.
MLP feature map sounds intimidating.
It sounds complex, but just think of it as a mathematical function
Okay.
that transforms the text from its original complex form into a more compact and efficient representation.
So it's like a high-tech compression algorithm for language.
You got it, and this
Yeah.
compressed information is much easier for the RNN to process, making the whole thing much faster and less memory intensive.
I see how the math is making this whole thing work.
Right.
But what makes this particular MLP feature map so special?
Well, remember how T2R starts with a pre-trained transformer?
Yeah.
So it's like they're building on the knowledge that the transformer has already acquired.
Right.
And this MLP feature map actually learns from the transformer's extensive knowledge base.
Wow.
It's essentially extracting its understanding of language
Right.
and encoding it in a more efficient way.
So it's like taking all of the transformer's expertise and distilling it into a more concentrated form.
Yeah, and here's where it gets really interesting.
Yeah.
The researchers didn't explicitly tell the MLP feature map
Yeah.
to copy the transformer's attention patterns. They just let it learn those patterns indirectly during this fine-tuning process.
Wait, so you're telling me this MLP feature map is figuring out the most important aspects of the text all on its own?
It is.
That's incredible. It's like watching an apprentice learn from a master craftsman
Yeah.
just by observing their techniques.
It is remarkable. And when they analyzed the attention patterns that emerged after fine-tuning,
Yeah.
they found that the RNN was focusing on similar parts of the text as the original transformer, but in a much more streamlined and efficient way.
Wow. So the RNN is basically mimicking the transformer's expertise, but using a shortcut.
Pretty much,
Yeah.
yeah. It's a very clever approach.
That's so clever. I'm really impressed by the elegance of this approach.
It is elegant. It highlights the power of combining, these pre-trained models
Right.
with these clever mathematical techniques
Yeah.
to achieve both efficiency and accuracy.
Okay, so we've kind of explored this mathematical foundation of T2R, and my brain is buzzing a little bit.
I bet.
But I'm curious, are there any, practical considerations when implementing this approach?
Yeah, that's a great question. So one of the key decisions that you have to make is choosing the right feature size
Okay.
for the MLP feature map.
Feature size. Okay, now we're getting really technical.
It's not as complicated as it sounds. Think of it like this. You're deciding how detailed you want those RNN notes to be. So a larger feature size means you're capturing more information,
Okay.
but it also requires more computational power.
Oh, so it's like a trade-off between the level of detail and efficiency.
Exactly. And what the researchers found is that the optimal feature size really depends on the specific task
Got it.
and how much accuracy you're willing to sacrifice.
Okay.
They even experimented with a hybrid approach where they kept some of the original transformer layers for tasks that required, the highest level of precision.
So it's all about finding the right balance for the job at hand.
Exactly.
That makes sense.
Another practical thing to consider is the computational cost of the fine-tuning process itself.
Oh, okay.
So while T2R dramatically reduces the overall, computational burden, training that MLP feature map still requires some processing power.
So it's not a completely free lunch.
It's not a completely free lunch. There's still some computational cost involved.
But it sounds like it's still a major win in terms of efficiency.
Oh, for sure. And especially as computer hardware continues to improve,
Right.
that cost of fine-tuning is going to become less and less of an issue,
Okay.
making T2R even more attractive for all kinds of AI tasks.
This is all incredibly fascinating. It feels like we're on the verge of a new era of efficient and accessible AI,
Yeah.
thanks to these techniques like T2R.
I agree. And in part 3 of our deep dive, we're going to kind of explore the broader implications of these advancements.
Okay.
Talk about the potential benefits and the challenges
Yeah.
of making AI more efficient and widely available.
That sounds like a great way to wrap things up.
Yeah.
Looking forward to part 3. Welcome back to the deep dive. We spent this whole episode talking about this cool new method for making AI models more efficient.
Yeah, it's called T2R.
Right, T2R. Where we're taking these resource-heavy transformers and turning them into these sleek, efficient RNNs.
Like those electric cars?
Exactly. And we even got a little technical right.
Yeah, a little bit.
We went into the mathematical underpinnings of how it all works. But now I want to step back and look at the bigger picture.
Yeah.
What does this wave of AI efficiency mean for the future? How's it going to impact the way we interact with AI in our everyday lives?
Right. Well, I think one of the most immediate benefits is going to be accessibility.
Oh, okay, yeah.
As these AI models become more efficient, they're going to be able to run on less powerful devices. So imagine sophisticated AI algorithms running smoothly on your phone, your laptop, or even tiny sensors
Wow.
embedded in everyday objects.
So instead of needing those huge data centers, we could have powerful AI right at our fingertips.
Exactly. And that opens up so many possibilities.
That's pretty amazing.
Yeah, think about it. Smarter virtual assistants that respond instantly, or real-time language translation.
Right.
That works even when you're offline.
Oh, that'd be a game changer.
Yeah.
No more waiting for that little spinning wheel, while your phone tries to catch up.
It's like the future is now.
Yeah, and I can even imagine applications in healthcare.
Oh, absolutely.
Like personalized health monitoring apps that give you insights and recommendations
Yeah.
based on your needs.
Totally. And it goes beyond just personal devices. Think about things like real-time data analysis in manufacturing.
Right.
For better quality control.
Okay.
Or predictive maintenance that could prevent costly downtime.
It's interesting.
Or even optimize traffic flow in smart cities.
Wow, so efficient AI could make everything run smoother and more intelligently.
It's true. It's like upgrading the world's operating system.
It really is. But with any powerful technology, we always have to think about the potential downsides.
Well, for sure.
Right. What are some of the risks that we need to be considering as AI becomes more efficient and more widespread?
Well, one concern is the potential for misuse.
Okay. Yeah.
As AI becomes easier to deploy, it also becomes easier to use for harmful purposes.
That makes
things like creating those super realistic deepfakes that are really hard to detect.
right.
Or even designing more sophisticated phishing scams
Oh, wow.
that could trick anyone.
So it's really important to develop safeguards as we're making these advancements right.
Absolutely. We have to be proactive
Mm.
and consider those ethical implications
Right.
of making AI more powerful and more accessible.
Yeah.
And this requires everyone to work together,
Okay.
researchers, policymakers, and the public,
Right.
to make sure that these technologies are used responsibly.
It's a delicate balancing act, isn't it?
It is.
We want to use AI for good,
Yes.
but we also have to be mindful of the risks.
You said it perfectly.
Well, this has been such a fascinating deep dive into the world of AI efficiency.
It has.
It feels like we're just scratching the surface of what's possible.
We are.
What other breakthroughs are waiting for us just around the corner?
Who knows? That's what makes it so exciting. It's such a rapidly evolving field.
Mm-hmm.
I think we're on the verge of a new era where AI is seamlessly integrated into our lives.
It's both exciting and a little bit mind-blowing at the same time.
It is.
Well, thank you so much for taking us on this incredible journey
Of course, it's been a pleasure.
into this world of efficient AI.
Mm-mm.
I'm feeling both inspired and a little bit overwhelmed.
That's great. Just remember, the most important thing is to stay curious, stay informed,
Yep.
and keep asking those great questions.
I will. That's a perfect note to end on. Thanks for joining us on the Deep Dive.